Okay, these are your guided notes for lesson 5.4. If you're intending on using these to fill out your notes, you are gonna need to be pausing this a lot because I don't plan on going slow enough. But hopefully you're watching this just to review the content, or if you're Jimmy, to actually learn it. So hopefully this will be helpful. We're talking about sampling distributions. A sampling distribution is a probability distribution, which we talked about last chapter. So just a list of things that could happen and the probability that it does happen. So it's a probability distribution of a sample statistic. It's formed when you take samples of a certain size, we're going to call that N, and it's when you take them repeatedly from a population. So if I have a class, I could repeatedly sample 3 of you and find out, like, say, your average height. So that would be the sampling distribution of your sampling means. I'd get a distribution of the average height from my sample of size 3. So this would be a visualization for it. So some population, this is representing everybody. I could keep taking different samples. They would all have the exact same size. Sometimes there are people who are in both samples, and that's fine. You're ultimately interested in the average of each sample that you would be collecting. So the properties, that's not what I meant to push yet. The properties of a sampling distribution of sample means. The mean of your sample means is going to be equal to the population's mean. So right now, my statistics class has an average height. There is an average for that population. That average is equal to the average that I would get if I would keep taking samples of size 3. If I would take 3 people, find their average height. I take 3 other people, take their average height. A different 3 people, average height. If I keep taking samples of size 3, finding those 3 people's average height, if I averaged all the averages I would get, it would be the same number as my population average. The standard deviation of your sample means, that's going to be denoted sigma sub x bar. That's equal to the population standard deviation divided by the square root of n. That's called the standard error of your mean. To illustrate this, I want to pretend we have 4 numbers, the numbers 2, 4, 6, and 8. Those are on slips of paper. They're in a box. I'm going to pick a slip, put it back, pick another slip so that I get a sample size 2. Before I do that, though, I want to know the population's mean, variance, and standard deviation. Now, it's a population, so I could just go to my calculator, put those 4 numbers in, and calculate those numbers. If you put those in your calculator like we did in Chapter 2, you would find that the mean of those 4 numbers is the number 5. The variance is the number 5, and the standard deviation would be the square root of that, which is, I don't remember what decimal it is, 2 point something. If you graphed those 4 numbers, if you came up with a probability distribution, you would have the number 2 here, which has a 25% chance of being selected. The number 4 has a 25% chance. 6 has a 25%. They're all uniformly distributed. Each one has an equal chance of being selected if you just have those 4 numbers on slips of paper. Now, if I instead take samples, so I'm not looking at just those 4 numbers, I'm taking samples of size 2, something different happens. So first I want to form that sampling distribution of my sample means. So for example, if I pick 2 numbers, I could pick 2 and 2, that average is 2. Or my samples could be the number 2 and then the number 4. The average of the numbers 2 and 4 is 3. My sample could be the number 2 and 6. That average is a 4. You could come up with every single possible sample and come up with the average for that. This is my sampling distribution, and I would like to organize that. I would like to see, well, first of all, the smallest mean that I see that came up is the 2. The largest mean is the 8. So I'm going to come up with a probability distribution with my means of 2 through 8. And I'm going to come up with their frequency. So I'm going to look. The frequency of a 2 showing up, there was exactly one time a 2 showed up. But a 3 showed up with a 2 and a 4, and then with a 4 and a 2. So it has a frequency of 2. The 4 has a 3. You can find the frequencies of all these. Back in Chapter 4, we said if we have a frequency distribution, we could come up with a probability distribution by dividing every frequency by the size of the sample. If you add all these frequencies, 16 things could happen. So you have a 1 in 16 chance of getting an average of 2. You have a 2 in 16 chance, you say 1/8. But that's the probability of getting an average of 3 from your sample of size 2. You can come up with all these probabilities and say, hey, look, I have a probability distribution. So we can find the mean, the variance, and the standard deviation of this using the stuff that we talked about in Chapter 4. So if you put your x values, the means, I guess, in L1 of your calculator, if you put these probabilities in L2 of your calculator, we said Chapter 4, if you take L1 times L2, then add up all of those products, you will get your mean. And if you do that in your calculator, which I would highly encourage because you're going to need it for this chapter, you're going to need it for the final, you get the number 5. Then we had said that the formula for the standard deviation of a probability distribution is every x value, subtract the mean from it, square it, and multiply by the probability. So I would suggest go up to L4, type in L1, which is where these are, minus 5, square it, and then say times L2, which is where your probabilities are. Then if you add all of those, you should get 2.5 out of your calculator, which means the standard deviation is the square root of 2.5, some decimal. Now, the distribution of these numbers, if you look at what's happening with my probabilities, as x increases, my probability increases, and then it starts decreasing. It is a symmetric distribution, and it kind of is resembling a bell curve, and that's not a coincidence. We'll come back to that in a second. So I want to compare these results with my population mean. We had said that the population mean, if I just put those 4 numbers in my calculator, I get 5, 5, and root 5. When we did it with the calculator with the complicated stuff, with all the 1/16th, the probability distribution, we got 5, 2.5, and square root of 2.5. This is not a coincidence. Earlier, we wrote down, and I would highly suggest you get on a note card, that the mean of your sample means, mu sub x bar, will always equal the mean of your population, mu. But the standard deviation of your sample means, S sub x bar, that is equal to the standard deviation of your population divided by the square root of your sample size. So it makes sense that these are not the exact same number here. What is happening is, if you take the square root of 5, which is your your population standard deviation, and you divide it by the square root of your sample size, we were taking samples of size 2. Well, 5 divided by 2 is 2.5. You get the exact same answer that we had. So you don't have to go through and actually take these samples. I'm just trying to illustrate to you what these 2 formulas that you need to have memorized mean. We're going to use these for the central limit theorem, which basically says that as your sample size increases, so as you keep taking samples of size 2, of size 3, of size 8, the shape of your distribution of the sample mean, taken with replacement, blah, 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 will approach a normal distribution, which is what I was pointing out, where it went from a uniform distribution to that bell curve, the symmetric distribution. And it's going to have that mean and standard deviation formulas we just talked about. So we could take something like this, something where I'm given population stuff. We could say that for the diameters of a tree, the mean is 3.5, the standard deviation is 0.2. But if I take random samples of size 16 from this population and find the mean of each sample, I want the mean and standard error of that distribution. Well, we just said that the mean of a sampling distribution is equal to the mean of the population. So we're still going to use 3.5 for the center. But the standard deviation of your sample distribution is equal to the population standard deviation divided by the square root of the sample size. So if I put that in my calculator, you're going to get 0.05. So that means my sampling distribution is still centered at 3.5. You can see that they're lining up. But instead of the standard deviation being 0.2, this one's a lot closer. My standard deviation is only 0.05. So you're taking the whole bell curve and kind of cinching it inward, but you're still getting something that's normally distributed. That's kind of like the key to what a lot of statistics second semester rests on. I'm just going to tell you that's what it is, and then we're going to try and do more application problems with it using the central limit theorem. This says if you have a sample size that's large enough, or if you're normally distributed, the central limit theorem will be used for sample means. So no longer am I going to say, what's the probability that someone is more than 62 inches? I'm going to say, what's the probability that a sample of size 10 has a mean that's more than 62 inches? The only difference is you're not going to use your old formulas for things, because we just said the mean's the only one that's the same. The standard deviation formula changed. which means the z-score formula changed. We can use this formula for your z-score now. But if you go back to the quiz that we took over 5.1 through 5.3, most of the time we don't find z-score first anyway. Most of the time we just jump into using your normal CDF. That's what we're going to look at in these last two examples. So this reported that certain kids watch an average of 25, so there's my average. It's normally distributed. I have a standard deviation of 3. 20 kids are selected. I want to find the probability that the average number of hours they watch is greater than 26.3. That's the key here. This problem is talking about the probability of an average. So it's different from the previous sections we were just talking about. Since I'm talking about averages, I'm talking about my sample distribution of sample means. These are the formulas you got to work with. So the mean of my sample means is still 25. Remember, those are always the same. But you cannot use the normal standard deviation. You cannot use the number 3 they give you. Because we're talking about sample means, you have to use 3 over root 20. So if you're going to find the z-score, use those two things. Otherwise, let's just jump right in and find the probability. When we find probabilities, we use your calculator's normal CDF function. So I'm going to do that. So the probability that my mean is greater than 26.3, I'm going to use normal CDF. Since I'm wanting it to be greater than 26.3, I'm going to use 26.3 as my lower limit. I'm going to say up to 1E99. I'm trying to say go up to infinity. They could watch TV forever. Or I guess I could find an upper limit. But either way, this will be fine. The mean is 25, and I have to use the standard error in place of my standard deviation because I'm talking about a sample size. And when you put that in, you get a decimal like we usually have. The main difference is noticing, hey, I'm talking about a sample here, sample means, rather than just a number being a certain thing. So here I've got a sample size 100. I want the probability that the mean time is between those two. So it's not just what's the probability that one person is driving for that length. It's the mean of my sample of size 100. So we're going to use the mean and the standard deviation given, but we're going to use them into these formulas. So we're going to use 25, but the standard error, the standard deviation of my sample means is going to have to be 1.5 over the square root of 100. So we're still going to use normal CDF. I'm still going to be looking between 24.7 and 25.5, but now I have to put in 1.5 over the square root of 100 for my standard deviation, for my standard error, because we're talking about a mean of a sample now. And then you still get an average, so 0.9768. So this is the assignment that goes with it. Good luck practicing it. It'll get hopefully more clear as you start doing more and more of it, as you see, oh, this one's talking about a sample mean as opposed to what we used to talk about, which is an individual value. So good luck.